Okay, hello students of third year secondary. This is physics session. My name is Ahmed and I teach physics. Today, inshallah, we are going to revise Unit 1. We know that Unit 1 involves Lesson 1, 2, 3, and 4. And for Unit 1, we are going to revise and have some problems concerning Unit 1, all of it. Let's read this example about Unit 1. Electric charge of 3.6 Coulomb passes in an electric conductor within 1 minute. If the potential difference between its terminals is 300 volts, calculate its resistance. Now, this is a simple direct question about how to calculate the resistance. We have electric charge, 3.6 Coulomb, passes in an electric conductor, and the time of this is 1 minute. We know that 1 minute has to be converted into 60 seconds. If the potential difference between its terminals is 300 volts, calculate its resistance. So for the answer for this, let's now consider the points that we have. Number one, we have the Q equal 3.6 Coulomb, and we have also time equal 60 seconds. The voltage is 300 volts, and what's needed is the resistance. Now, the first thing is we know that the electric current intensity equals Q over T. Q is the charge, amount of charge, and T is the time. We have Q equal 3.6, and we have the time 60 seconds. All we have to do is to divide 3.6 divided by 60, and the current will be 0.06 ampere. It's direct application, and we don't have to do anything, just we converted the time from minutes into seconds. Now, what's needed here is R. R equals V divided by I. This is from Ohm. This is Ohm's law, direct applications. The V is 300, and the current is 0.06. So when I divide 300 by 0.06, it gives me 5,000 ohm. Direct applications, all we have to do is to apply, get the electric current intensity, and then to get the electric resistance. All right. In multiple choice questions, you might be given 5 kilo ohm, which is the C. So don't be intimidated or scared when you have the multiple choice answer does not match your answer, because sometimes it gives you different units. So 5,000 ohm is equal to 5 kilo ohm. Okay, let's now consider another example. A wire of length 20 meter and its cross-section area is 0.1 millimeter squared. If the potential difference between its terminals is 10 volts and the current intensity passing through it is 0.5, which is half ampere, calculate A, the resistivity of the wire, B, the conductivity of the wire. All right, we know that the first step is to extract information. The length of the wire is 20 meter, and cross-section area is 0.2 millimeter squared, and we have to convert here the millimeter squared into meter squared, just to work with the SI units. Okay, the potential difference, we don't need to convert the potential difference. And the current intensity is 0.5 ampere. We don't even need to convert anything. And calculate A, resistivity of the wire and conductivity of the wire. And I think they are related somehow to each other. So we start here for putting the answers. We have here the length 20 meter. And the cross-section area is 0.4 times 10 to the power of -6 meters squared. Now, converting millimeter into meter, all we have to do is to multiply by 10 to the power of -3, and I have power 2, so 2 times 3 equals 6. So I convert from millimeter squared into meter squared just by putting 10 to the power of -3, but we have the bracket outside is power 2, so this gives me -6. So A is 0.2, 10 to the power of -6 meter squared. The potential difference between the terminals is 10 volts, and the current intensity passing through it is 0.5 ampere. All right. What is the resistivity? Rho sub E. And conductivity sigma. All right. So we start by calculating the electric resistance. And we know from Ohm's law that R equal V over I. This is direct application from Ohm's law. And do I have the resistance? Yes, I do. It is 10 ohm. Do I have current intensity? Yes, it is half ampere. So I divide the voltage 10 by the current intensity, which is half, to give me 20 ohm. Now, I have now the resistance. I need to apply now the resistivity law. Resistivity equals R A over L. What is R? The electric resistance. What is A? Cross-section area. And what is L? The length of the wire. Now, I calculated R. I just put its value, which is 20. I have A cross-section, which is 0.2, 10 to the power of -6. This is the cross-sectional area. And the length of the wire is 20 meters. So I just plug in the numbers, and I have at the end, if I calculate it using calculator, I have resistivity rho E equals 2, 10 to the power of -7 ohm meter. Okay. Don't forget to put the units. The unit of resistivity is ohm meter. All right. We know also that resistivity is the reciprocal of conductivity. The relationship between them is both of them, they are inversely proportional to each other for the same material. Sigma is the electric conductivity, is 1 over rho sub E. This means that the conductivity is the reciprocal of resistivity. Okay. So to calculate conductivity, I just put 1 over resistivity value that I obtained, which is 2, 10 to the power of -7. And the result, if I plugged in the number, it would be 5, 10 to the power of 6 ohm, -1 meter, -1. We know that the conductivity is the reciprocal of resistivity. So the unit also is the reciprocal of the unit of resistivity. So conductivity unit is the reciprocal of resistivity unit, which is ohm -1 to the power -1 and meter to the -1. So after all of this, we have the final result is conductivity is 5 times 10 to the power of 6 ohm, -1 meter, and -1. Okay, this is another example of how to apply Ohm's law with getting the resistance and resistivity. And also it involves the relationship between conductivity and resistivity of wires. Now, here you have another example. Example number 3 says, if the electric potential difference between the ends of an electric bulb is 75 volts, and the electric current intensity passing through it is 1.5 ampere, then calculate the electric power of the electric bulb and the consumed electric energy when it lights for 10 minutes. Okay, we know before that electric power is related also to the current intensity, and it's also related to the kind of connection of the circuit. So all we have to do to start with this is to extract the information from the problem itself, and then try to connect the information with each other with mathematical formula to calculate what's needed. So let's start now step by step. The first thing he says that the electric potential difference between an electric bulb is 75 volts. So this is V equals 75 volts. All right. The electric current intensity passing through it is 1.5. What do I have now? I have voltage and I have current. All right. What's needed is calculate the electric power. All right. So having the voltage and also the electric current intensity will make it easier to calculate the electric power. And also he wants the consumed electric energy when it lights for 10 minutes. So he wants the electric power. And after we calculate the electric power, he also wants the electric energy if the light continues to give out light for 10 minutes. I don't need to convert to anything. All of them, they are actually the units I want, except one thing, which is the time. The time is here by minutes, so I have to convert it into seconds. But all the other quantities are with the units I want. So let's now see step by step how we are going to proceed. The first step, as we said, we have voltage 75 volts, and we have the electric current intensity 1.5 ampere, and we have the time 10 minutes. What does he want? He wants the power, and he wants the also he wants the energy, electric energy, or the work, energy and or work. All right. We start first by the electric power. We have many formulas to calculate the electric power according to what's needed. So for example, electric power equals VI, because he gave me voltage and he gave me the electric current. So the formula suitable to calculate the electric power is P sub W, or the power, electric power equals the product of voltage multiplied by electric current. So he gave me the voltage, all right, which is 75. He also gave me the electric current intensity, which is 1.5 ampere. So if I have voltage and I have current, and he wants the power, the only thing I need to do is just multiply both of them. So simple multiplication, and I don't need to convert to any units because I have the units the way I need it. Voltage in volts, current in ampere, so I don't need to convert. So I will here multiply 75 times 1.5, and the result will be 112.5, and the unit of power is watt. Okay, and for short W, or you can write WATT, for like, but pay attention, the unit of power is watt, and W stands for watt. Okay. Now, the second requirement he wants is the consumed electric energy, all right, by this bulb if the light goes on for 10 minutes. So I previously calculated the electric power. So I have the electric power, and he wants the energy consumed when this bulb continues to give out light for 10 minutes. So I will use the electric power value that I have obtained before, which is 112.5 watts. And I will use also the duration of time for this bulb to give out light. And this duration is 10 minutes. So if the bulb has a power 112.5, and it will continue giving out light for 10 minutes, what is the energy consumed? We know that the energy equals power multiplied by time. So I have the power. Yes, I do. 112.5 watts. Do I have the time? Yes, I have 10 minutes. But I cannot keep the 10 minutes the way it is. I have to convert it into seconds. So I multiply by 60. So the total thing is I will multiply now the power, 112.5 times 10 times 60. Now 60 is the conversion factor to convert from the unit of minutes into unit of seconds. And after doing the calculations, I will have the energy, or the work, is 6.75 10 to the power of 4 joule. Joule is the unit of energy, or the unit of work. Okay, so this is another example of how to apply or how to calculate the power and the electric energy if I have the needed one, like current and voltage. Example number 4. A coil of cross-section area 0.3 meters squared is put in a uniform magnetic field of density 0.05 Tesla, calculate the magnetic flux which passes through the coil when the coil is A, perpendicular to the magnetic flux, B, making angle 30 with the magnetic field. All right, so let's take it step by step. I have a coil now, okay? I have a coil, and for this coil, I have its cross-section area. And I have V, which is the electric current in the magnetic flux density. What does he want? The magnetic flux. Okay, when it is perpendicular. So let's start first by extracting information. So here I have the 0.3, 0.3 here. This is 0.3 here meter squared. And I have the electric current, the magnetic flux density is 0.05 Tesla, and he wants the magnetic flux phi sub m. We know that phi sub m or phi m magnetic flux equals BA sine theta. This is the rule. We just put it, phi sub m equals BA sine theta, and we have B 0.3. We have A 0.05, and he said perpendicular. Now, the word perpendicular means that theta is 90. Okay, so I will just write it as sine 90. So the word perpendicular means that theta equals 90. I just put the numbers 0.3 times 0.05 times sine 90. And if I multiply all these numbers together, and as you know that sine 90 equal 1. So it is as if I multiplied 0.3 times 0.05, and the result will be 0.015 Web. Web stands for Weber, which is the unit of magnetic flux. Now, the second part of the question saying, if the coil is making an angle 30 with the magnetic flux. So before he wants us to calculate it when it is perpendicular. Now he wants us to calculate it when it makes an angle 30 with the magnetic flux. So in this case, I put the same rule, which is phi sub m equals BA sine theta. So I have B 0.3, I have A 0.05. All I have to do is, instead of sine theta, I put sine 30. All right. And we know that if I plug the numbers and I do everything, so I will get phi m equals 7.5 10 to the power of -3 Weber. All right. So this is the magnetic flux he wants, 7.5 10 to the power of -3 Weber. All right. Let's now consider the question number 5, which says, two parallel wires 30 centimeters apart. A current of 40 ampere passes in the first wire, while 20 ampere passes in the second. Calculate the magnetic flux density at a point at 20 centimeters apart from the first wire when the current in the two wires is. So the first case, the current is in the same direction. I have two wires and the current in the same direction. B, if the current in opposite direction. And he gave me that mu, which is the magnetic permeability, equals 4 pi 10 to the power of -7 Weber per ampere meter. All right, so let's now extract the information and see what's going on. We need to draw the diagram of what's going on just to have an idea of what the question is all about. So the first thing is I have two parallel wires. So two parallel wires, and the distance between them is 30 centimeters. And both two wires are parallel to each other. Now, I have current passing in one wire, say the first wire, 40 ampere. And I have 20 ampere passing in the second. All right, so what does he want? He wants us to calculate the magnetic flux density at a point, and this point is 20 centimeter apart from the first wire. So actually, if I look at it without drawing the diagram, I will not comprehend what's going on. So I advise you, if you have question like this, I advise you to draw a diagram for your brain to think about it. Now, here I have the two wires. The wire on the right is the first wire, say, and say the second wire is to the left. And current passing in the first wire is I1, current passing in the second wire is I2. And as you see, the distance between the two wires is 0.3 meter. What does he want? He wants us to calculate the magnetic flux density at a point. This is the point he wants, okay? Can you see now the cursor? Can you see I point at, this is the point he wants, okay? Now, this point is 0.1 meter from the second wire, but it is 0.2 meter from the first wire, all right? Now, B1 is the magnetic flux density in like near I1, and B2 is the magnetic flux density near I2. All right, just drawing the diagram or drawing the question will give your eye a better way to think about the problem itself, because to just try to figure out where is exactly the point he wants us to calculate the B at. This is the point. If you look carefully at the point on the diagram, you understand where exactly I have to calculate the magnetic flux density. Okay, let's proceed. First step is extract information, and here I have I1 equal 40 ampere, I2 equal 20 ampere, X equals 0.3 volts, all right? And here you have D1, I don't know, and VT, I don't know. VT is the total current density. Let's now proceed after knowing what exactly we have to do. The law says to calculate the magnetic flux density, like near any point near a wire, the law says that B equals mu I over 2 pi D. Mu is the magnetic permeability, I is the current intensity, and D is the distance from the wire to the point I want to calculate B at. So let's say now I have the two wires. Calculate the first density, the flux density of the first wire, B1 equal mu I over 2 pi D. So mu equal, from the definition or from he give me that it's equal to 4 pi 10 to the power of -7. This is mu, and I is 40. Where did I get this from? From the given. He gave me this. Divided by, the denominator is 2 pi. I put it as it is. And the distance is 0.2. Where is 0.2? Here. I go back at the diagram. Where is 0.2? This one. All right. This is the first wire, the I1. And this is the point I would like to calculate the flux at. So the distance is 0.2. All right. So back again to the question answer. So if I plug in the numbers, and be careful when you calculate the numbers with each other, I will have the final answer is 4 times 10 to the power of -5, and the unit of B is Tesla. Now, as I did for the first wire, I am going to do the same process for the second wire, all right? But I have to look at the distance, because the distance now will change, and the current also will change. So what is B2? It is the magnetic flux density resulting from the second wire, okay? Which means that I have to consider the electric current passing in I2, not I1. So look here, a current of 40 ampere passing in the first wire. So when I calculate B1, I consider 40. But when I calculate B2, I consider 20. Why? Because 20 ampere is the current passes in the second wire. Okay, so back again to the question. B2 equals 4 pi times 10 to the power of -7. What is this? This is the permeability, magnetic permeability, which is constant, times I. What is I? 20. Why 20? Because this is the current intensity passing in the second wire. Divided by, I have here 2 pi, I put 2 pi as it is. And the distance is 0.1. Back to the diagram. Where did I get this from? 0.1 is here. This is the distance between the point I would like to calculate the magnetic flux density at, which I point at it now, and the wire I2, the wire that's the second wire. So back again, this is 2 pi times 0.1. Now I put all the numbers and I calculate it. I will have V2 equals 4 times 10 to the power of negative 5. Okay, which means that V1 equal V2. Look at here, 4 10 to the power of negative 5 Tesla. V2 also 4 10 to the power of negative 5 Tesla. So they are equal. But that's not what's required. What's required is he wants the total magnetic flux density, BT, the total. Now, the total equals B1 minus B2. Why B1 minus B2? Because he said, look at the question itself, he said what? In the same direction. When it is in the same direction, the current in the same direction inside the two wires, it means that the total flux density in between them, I have to subtract. I subtract because the point I consider is between the two wires. That's why I have to put negative. Don't be confused between this. So the total magnetic flux density, BT, because the point is inside or between the two wires, I have to consider B1 minus B2. Why B1 minus B2? Minus because the point is in between the two wires. So in this case, I put the value of B1, 4 times 10 to the power of negative 5, and I subtract it from 4 times 10 to the power of negative 5, and it will give me 0. All right? So the total magnetic flux at that point equals 0, which means that it vanishes. I have no magnetic flux density at that point. Now, the second requirement in the question, he says he wants the total magnetic flux, calculate the magnetic flux density if the current is in opposite direction. Now, the same point, everything is the same, but the current will reverse in one wire, which means that they will not be in the same direction. When they are not in the same direction, simply what I do is I add the two magnetic flux densities. So B total equal B1 plus B2. Pay attention. If the current passes in the same direction and I would like the total B between the two wires, I subtract. Okay? But if I would like to get the total magnetic flux density between the two wires and the current passes in opposite directions, I add them to each other. All right? So here the total B is B1 plus B2, which is equal to 4 10 to the power of negative 5 plus 4 10 to the power of negative 5, which will give me 8 10 to the power of negative 5, and the unit is Tesla. All right, simple application of how to proceed and how to calculate things from the question. As you see here, drawing the diagram of the question sometimes helps us to figure out the correct distances and also to comprehend what's required. All right. So I think by this we come to the end of our revision for Unit 1. We revised today problems and questions concerning Lesson 1, Lesson 2, Lesson 3, and we moved on to also the magnetic flux density concerning two wires. I would like you to continue, inshallah. If you have any questions, don't forget to drop it. My name is Ahmed. I teach physics, and see you next time. Thank you for listening, and take care.